We need to get through a little bit more terminology so we can understand what we're talking about when we're dealing with probabilities. A very important concept is the idea of a sample space. A sample space is simply the set of all possible outcomes in an experiment. So consider tossing a coin, just a single coin. If you take a single coin, what could happen? Well, you could see a head or you could see a tail. This is the sample space. And these these brackets, I kind of scribbled them fast because that's the way I write them. But you properly, it's this bracket. You see it on your keyboard. But that's the way I kind of quickly scribbled them. It's set notation is what it is. And very commonly we use S to represent the set of the sample space. So in a simple coin experiment, this would be the entire sample space. Think of the sample space as your universe. Your universe for a particular experiment. This is everything that could possibly happen. Now a simple sample space is one in which all possible outcomes have equal probability, such as tossing a coin. If you have, this actually assumes you have a fair coin. If you have a fair coin, then a head is equally likely to a tail. The outcome of craps, as example, is not a simple sample space. Now, if you're not familiar with craps, it's a dice game. You take two dice and you roll it. And the probability of getting a 2 is not the same as the probability of getting a 7. Now, if you roll two dice and add them up, the smallest you can get is a 2, because 1 and 1 is the smallest that you can get in both coins. 1 and 1 is 2. And the biggest you can get is a 12, because the dice have, the largest number on the dice is a 6. And actually, we're going to enumerate the sample space for craps shortly here. I think in another video. So this notation n of s is used to indicate the number of elements in the sample space. Now this is function notation. If you remember from algebra the idea of function notation, you may use f of x. It's a function of x. This is not f times x. N of s equals the number of elements in S. In this case, S is our sample space. This is not N times S. This is not multiplication. That's a big no-no. It's a very common mistake. That is not multiplication. It simply refers to, as a function notation, the number of elements in S. Now another piece of common terminology is the idea of an event. We will be talking a bunch about events. Now event is actually any subset. Think of a subset as any combination of a sample space. So before we think about tossing 3 coins, let's go back to simply 1 coin. We said the sample space was heads and tails. So here there's only 2 possible events. Either you observe a head, that would be one event. So maybe event A equals observe a head, and event B is observe a tail. Those are the only 2 possible events in this sample space. But consider tossing 3 coins, and I want the event A to be observe 2 heads. Well, let's list the sample space and see what's going on here. Now the easiest way I think to list a sample space of this nature is with a tree diagram. Here's the basic idea behind a tree diagram. I'm going to start here, and then I'm going to say, what happens if I toss my first coin? Remember, I have 3 coins here. Well, if I toss that first coin, there's 2 things that could happen. I could get a head, or I could get a tail. That's everything that could happen in that first coin toss. Now, if the first toss was a head, and I toss a second coin, what could happen? Well, the second coin could be a head or a tail. Now, if this first toss was a tail, and I toss a second coin, what could happen? Well, again, I could get a head or a tail. What we've actually done is we've enumerated the sample space for tossing 2 coins. I could get a head head, a head tail, tail head, and a tail tail. We can see every possible combination here. But we want 3, so we're going to take this out one more time. So if I got a head on the first coin, a head on the second coin, what could happen on the third? Well, there could be a head or a tail. Likewise, following the path this way, if I had a head on the first coin, a tail on the second coin, what could happen? Well, I could have a head or a tail. I think you can see the pattern here. This keeps going. And what I've done here is I've actually enumerated, by following these paths, every possible outcome. Well, what could happen here? I'm going to set up a little table here. And I'm going to say, I'm going to call this H for heads. And I'm going to say the probability of H equals H. Now that may seem a little bit confusing to you at first, but what this is capital H is the main variable I'm using, and the little h is simply saying this is the number actually observed. This notation, it may seem a little awkward now. We actually get into it much more in a later chapter. But this is simply saying the probability of heads. So, how many heads could I observe? I could observe 0, I could observe 1, I could observe 2, or I could observe 3. That's what could actually happen. So, let me see here. Let's follow this path. I have head, head, head. So I just took care of this path. So under 3, there's one way to do it. I could have head, head, tail. That's 2 heads, right? So under 2, there's one way to do it. Took care of that path. Head, head, tail, found this path. So that is another way to do it. Head, tail, tail, that's 1 head. So that's one way to do it. And then following this path, have tail, head, head. That's 2 heads. So that's another way to do it. They have tail, head, tail. That is 1 head. So that's another way to do it. Here you have tail, tail, head. That's another 1 head. That's another way to do it. And then I have tail, 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 which is no head. So there's one way to do it. So out of here, there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 different combinations. So the probability that I observe no heads is actually 1 out of 8. The probability to observe 1 head is actually 3 out of 8. Probability of 2 heads is actually 3 out of 8. The probability of 3 heads is actually, all heads, is 1 out of 8. Now what I use for this is right here. The probability of an event is n of a, just like n of s is the number in the sample space. Here there's 8 possible things that could happen in the sample space. N of a is the number of ways the event can happen. This is not n times a and n times s. We do not cancel out like that because this is not algebra such as function notation. So at first I said, okay, I want the event to be no heads. Well, there's only one way that could happen out of 8. Then I said my event is now 1 head. Well, there's 3 ways that can happen out of 8. Then I said, well, the event is 2 heads. There's 3 ways it could happen out of 8. And then again, I said, 3 heads, there's only 1 way it could happen out of 8. So using this to calculate the probability of an event, I simply named each of these events individually and calculated the probabilities. So let's go back to actually listing the sample space as such. I need just a little bit more room here. So my sample space, using this, I'll have a head, head, head. I have a head, head, tail. Let's follow this path. I have a head, tail, head. And then I have a head, tail, tail. Then I have a tail, head, head. And then I have a tail, head, tail. And then I see that was tail, head, tail, 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 head. And then the last tail, tail, tail. Count them 1, 2, 3, 4, 5, 6, 7, 8. Yeah, I got them all. So this is actually my sample space right here. This lists everything that could possibly happen. And then these probabilities I found up here earlier, I could get it out of this just as easily. There are 8 possible outcomes, and I want the probability of getting, say, 2 heads. Well, see, there's 1, 2, 3. There's 3 out of 8, which is what we said right here. Now, consider actually tossing a single coin 10 times. If I were to actually do it, I'm going to add the hat here because it's an experiment now. So the probability, the empirical, the experimental probability of getting a head in 10 tosses will be the number of heads that I observed divided by n, which would represent the number of times I actually ran the experiment. Now again, this is function notation. We can't cancel n's. That doesn't make any sense here. This is simply function notation. And I actually did that a little while ago. I grabbed a quarter and flipped it 10 times just to see what happened. And what I found is that the probability of a head, based on flipping a quarter 10 times, I ended up with 7 out of 10, which is obviously 0.70. Now in theory, this should not have happened, but 10 is actually kind of a small number, so who knows what's happened for sure. But in theory, the probability of getting a head is actually 1/2 of a single coin, because the sample space would be simply heads, tails. And we're assuming that this is a fair coin, so the probability of a head equals the probability of a tail. So the probability is going to be 1/2. If I do it 10 times, then 1/2 times 10 is 5. So I should have observed 5. So I should have had 5 out of 10. Theoretically, that's what it should have happened. But when I actually did it with my quarter, this is what I observed. Well, if I grab that quarter again and do it again, I could get 7 out of 10. But more likely I get something else. I may actually get 5 out of 10 or 6 out of 10 or 4 out of 10. It would vary, every time you do it. However, if I were to toss that same quarter, say 1,000 times, that would be another story. If I toss that quarter 1,000 times, I'll be very, very surprised if I got 70% heads. I would expect much, much closer to 50%. I would not expect exactly 50% because it's experimental. There's going to be some randomness going on, but I would expect much closer to 50%. Now this is an extremely important concept. Probabilities always reside on 0, 1. By reside, I mean the smallest value you can have is 0, and the largest value it can have is a 1. Now this is a reminder from algebra. These square brackets mean that 0 and 1, the endpoints, are included. If I wanted to exclude 0 and 1, I'd write it like this. This means 0 is excluded from the interval, 1 is excluded from the interval. But that's not what we have here. What we have is the endpoints are included. What this means is that 0 is the smallest possible value for a probability. It is not possible to have a negative probability. 0 is the smallest. Likewise, 1 is the largest possible value for a probability. It's not possible to have a probability greater than 1. 0 simply means that an event never happens. So if I had a coin, I told you the probability that if I flip this coin, the probability of a head equals 0. What that's telling you is to have a two-tailed coin, because that's the only way that could possibly happen. If the probability of an event is 1, that means that event always happens. So again, if I told you the probability if I flip a coin is 1, what I'm telling you is I have a two-headed coin. Now in reality, we don't typically see probabilities of 0 and 1. We see all kinds of ranges because there's an infinite number of possibilities in between. Now, this is important. It's mathematically impossible to have a probability smaller than 0, which means negative, or greater than 1. Why? Well, let's go back to our definition of probability. We said the probability is a number of times the event occurs divided by the number in the sample space. Well, if it never occurs, it's going to be 0. The number in the sample space will always be at least 1. In other words, this is always going to be positive. That's going to be a positive number. Well, 0 over any number other than 0 is 0. See, neither of these are negative. Something cannot happen a negative number of times. And because the sample space, the number observed is always going to be positive, I'm going to end up with 0. It's not possible to be negative. Likewise, suppose that the event A always happens. If it always happens, that means it's equal to the number that's actually in the sample space. So the number in the sample space over the number in the sample space, and by the way, both of these obviously have to be positive numbers, gives me a positive 1. It's impossible, it is mathematically and theoretically impossible to get a probability greater than 1. Now, this is extremely important for students that are in my class. If you're in someone else's classes, watch these videos and check with your professor. But here's the idea. If you have a quiz problem or exam problem or something you're working on, and if you report a probability that is either less than 0, meaning a negative, or greater than 1, if you report either of these, if the problem's worth 5 points, you will lose 6 points, or 7, depends what mood I'm in at the time. My rationale to that is if you can do something impossible, so can I. So this is extremely, extremely important. Actually, there's one other place in the courses that I teach that you can actually get negative points by doing something. And that comes up much later in another chapter, and I'll talk to you about that later when you get there. Definitely give you a full warning. But if you report a negative probability or a probability greater than 1, that is absolutely mathematically impossible, and you will lose more points than what are possible for that particular problem. I hope that really drives home the idea that probabilities reside on 0, 1. An extremely important concept.